So before we get started, just a couple of things. First of all, fire exits are over here and over there. We're not expecting fire, but if you do need to leave, I would recommend that one because it is the closer way out. And if you do need to leave at any point during the talk, you're welcome to just head out that way as well. You can just push through the doors and you'll find yourself back in the main visitor area. And then if you want to come back in, you can just push through the doors again and come back in here and go back to your seat. Absolutely no problem. Now, I do want to just ask you guys, please raise your hand if you've heard of gravitational waves before today. Okay, not many people. Okay, please raise your hand if you know what a gravitational wave is. 4 people in the front. Okay, well, we're going to hopefully change that. We're going to hopefully by the end of the talk, you guys will all have a good idea of what gravitational waves actually are. And also, I think you'll agree with me when I say that they are incredibly cool. So, to start off with, I'm going to do a bit of an introduction. And first of all, I want to talk about why we're doing this today. And that's because of this thing here. So this is a diagram of the first observation of gravitational waves, the first time we were ever able to detect these signals coming from space. And it was this gravitational wave, it's called GW150914. It looks like just a bunch of numbers, but this is just GW for gravitational wave and then the date. So this is the 14th of September 2015, or 10 years, 1 month and 11 days ago. So we have just passed the 10-year anniversary of the first direct detection. And this was using the LIGO gravitational wave detectors, which are based in the United States. So we're going to kind of celebrate this by first of all asking, what are gravitational waves? How did we get this idea that these things might exist? And what was the journey from going, okay, gravitational waves might be a thing, all the way up to discovering them 10 years ago? And then look at the science we've done over the last decade. What kind of gravitational waves have we discovered? What have we learned in this time? Where are we going in the future? And why are these so important? And this final question can be answered pretty well with this quote right here from Professor Stephen Hawking, who you might have heard of before. There are only 2 types of waves that can travel across the universe, bringing us information about things far away: electromagnetic waves and gravitational waves. Electromagnetic waves, also known as light. So this is things like radio waves, microwaves, infrared, X-rays, visible light that we know of, ultraviolet gamma rays. All of this is electromagnetic radiation, and this is how we do all of the science that we do pretty much in astronomy. Gravitational waves are an entire other way to see the universe, and they are pretty awesome at doing that. And I just wanted to say as well, I do have a little bit of background in gravitational waves. So I studied astrophysics at university, and my master's thesis was on using gravitational wave detections to try and make measurements about the rate of expansion of the universe. This isn't something that we can do right now, but it is something that we can potentially do in the future with our next generation of even more advanced detectors. So I think gravitational waves are awesome, and hopefully you guys will as well. So let's dive into it. And we're going to start off with a few things that are good to know for the talk tonight, because some of you guys might know a bit about science and astronomy already, some of you guys might not do. So the first thing we're going to talk about are light years. We do not use kilometers for distances in the night sky or in space because it makes absolutely no sense at all. So for the rest of the night's talk, we're going to use light years. Now, 1 light year is the distance light can travel in a year, and light is the fastest thing in the universe, so this is a pretty big distance. It equates to 9.45 trillion kilometers. If we put this another way, then Neptune, the furthest planet from the sun, is 0.0005 light years away. Alpha Centauri, the closest star system to our solar system, is 4.4 light years away. The Andromeda Galaxy, which is the closest major galaxy to our Milky Way, is 2.5 million light years away. And then the closest gravitational wave that we've detected so far was 144 million light years away. So we are looking at enormous distances in space when we are detecting gravitational waves, millions or billions of light years. This is the point where you should try and just not try and understand what this means, just accept these numbers and we try and move on with our lives. The other big numbers that we need to accept are solar masses. So when we're comparing the origins of gravitational waves, we are looking at things like black holes, which are really heavy. And we don't use kilograms for black holes, just like we don't use kilometers for distances in space. Instead, we use the much more sensible solar masses. So our sun weighs 1 solar mass, or 2 times 10 to the power of 30 kilograms. So that is a 2 followed by 30 zeros. Pretty enormous. So if something is 10 solar masses, that means it weighs 10 times more than our sun. If something is 100 solar masses, it's 100 times more than our sun. You get the idea. So hopefully this will make things make a little bit more sense just by comparing them to our sun. And I did briefly mention black holes. These are the number one sources of gravitational waves that we are detecting. Black holes you might have heard of before, but you probably don't know much about. They are really simple objects. We describe a black hole with a singularity. It's a single point in space that contains all of the mass, all of the stuff of that black hole condensed down into something that is infinitely small. And if that thing sounds hard to imagine, then it is. It is very hard to picture what a black hole actually means. But we do know that they have this very strong gravitational pull, so strong that once you get to a certain distance from that singularity, you're going to be pulled in with such a strength that nothing can escape, not even light. And this is what creates the event horizon going around a black hole. This is the black bit where light can enter, but light cannot exit, so it is just completely dark. And black holes are a type of compact object, which are the corpses of stars. So when you have an average star, like our sun, it's going to go through this life cycle, and it's going to form something called a white dwarf, which is about the same size as the Earth, but contains anywhere from 0.5 to 1.5 solar masses. So they are really dense things. A teaspoon of white dwarf weighs about the same as an elephant, for comparison. When you have a really big star, it follows this life cycle here, becoming a super red giant, exploding in a supernova, to then form a neutron star, which is like a white dwarf, but even more extreme. Something the size of a city, but containing between 1 and 3 solar masses. So a teaspoon of neutron star weighs about the same as all of the atoms of humanity combined. So they are incredible. And black holes are even more extreme. So for the most massive stars here, we get black holes being created, which are infinitely dense. So they are pretty awesome as well. Now, gravitational waves, we'll come onto this later, but these are really, really weak. In fact, they are very hard to detect at all. The only gravitational waves we can detect are some of the strongest in the entire universe, which comes from the cataclysmic mergers of neutron stars and black holes. So it's this really extreme objects smashing together, generating these enormous ripples through space-time, which is the only things that we're able to actually detect at the moment. But we will talk about that a bit more later on. Now, I'm going to be checking in with you guys throughout the tour. So first of all, does this all make sense? Do you guys have any questions at this point? Yes, go for it.
Why the size matter whether it becomes white dwarf or black hole?
Yes, so it's to do with the mass, the amount of stuff that's there. So what's happening at the end of the star's life is the core of that star is collapsing down under gravity. So gravity is pushing everything inwards. And the star is going to sort of try and stabilize itself. So for a white dwarf, it stabilizes itself by having all of the electrons pushing against each other to stabilize against gravity. So it's going down and down and down and down, then it stabilizes, and then you get a white dwarf. If you've got an even bigger star, it's compacting down and down and down and down. It tries to stabilize to become a white dwarf, but gravity is still winning. So it keeps on going, gets smaller and smaller and smaller, and then it does eventually stabilize itself by having neutrons pushing against each other. So these other building blocks of atoms. And then if it's even bigger than that, not even the pressure of these neutrons can stabilize it. So it keeps collapsing down as far as it can go to form a black hole. So it's about kind of how strong is the gravitational force at the moment of the death of this star. That is what gives us the kind of which corpus of the star we're going to get. Does that kind of make sense? Kind of. Hey, yes?
Yeah, recently, there was speculation that there's interstellar communications, right? Did you?
I'm not aware of this, no. As far as I'm aware.
That is just so would that kind of communication be in a way related to this gravitational waves?
So one of the first ideas of gravitational waves was that they could be used for communications by really advanced civilizations. But we have no evidence that that has actually happened. We have no evidence that this could happen in the universe. It is just a potential idea. Yeah. Okay, so let's talk a little bit more about the gravitational waves then. Let's talk about the origin of these phenomena. How do we get these ideas that gravitational waves even exist in the first place? And the origin of this starts in the 1860s with this guy here, Scottish physicist James Clerk Maxwell, one of the most important physicists of all time, mainly for his work formulating these equations here, which we know of as Maxwell's equations. And this set of 4 equations very elegantly describes all of classical electromagnetism. So anything involving electricity, like circuits and currents, anything involving magnetism, electromagnets, power generation, regular magnets, and light as well, can all be explained in a classical sense by these equations here. So this was incredibly influential, this work. But there is a bit of a problem that happens when you try and apply Maxwell's equations at different speeds. If I'm traveling one speed, you guys are traveling at another speed, and we try and solve these equations together, we're going to get answers that are inconsistent with each other. And this goes against our kind of normal understanding of how speeds work. So to demonstrate this, I have my friend Marina, one of the night guides here at Dark Sky Project, who is a very talented skier. And she's also a very adventurous skier as well. So Marina has decided to ski on a train. So when we are watching Marina ski on the train, we see the train moving in this direction with one speed, v1. We see Marina moving in this direction with another speed, v2. So we go, okay, how fast is Marina moving? If she is moving at this speed, and the train is moving at this speed, we add them together and we find that in total they're moving at the speed v3. This is how we intuitively understand the universe around us in our day-to-day lives. Speeds add together. But if you do this for Maxwell's equations, you get answers that don't work. So that is a bit of a problem because everything is in motion. We move around on the Earth spins around on its axis, it moves around the sun moves around the Milky Way, and the Milky Way is in motion as well. So everything is moving all the time, and all of our experiments give us consistent results day to day. So we have something called the principle of relativity. The universe does not care what speed you're traveling at, or the fancy physics way. It doesn't care what reference frame you are in. It's going to give us consistent physics throughout. So does this mean that Maxwell's equations are wrong? Well, no. The thing that is wrong is actually this idea that we can just add speeds together. And it turns out that the only way to make Maxwell's equations make any sense between different speeds, between different reference frames, is using this set of equations here called the Lorentz transformations. So this is telling you how time and then the free spatial dimensions change depending on your speed. And then we had this guy coming along, Albert Einstein. And in 1905, he formulated his theory of special relativity. What he did was he took two ideas. First of all, the principle of relativity, that the universe must make sense no matter what speed you're going. And second of all, that the speed of light is constant. This also must be true. It is predicted by Maxwell's equations, and if the speed of light is not constant, then matter and energy are completely meaningless, which wouldn't be very good. So from these two ideas, he was able to arrive at the idea that these equations here describe our universe. So we are in a universe described by these equations, and this is telling us that space and time are not the same for everyone. If you're traveling at different speeds, you're going to experience these things differently, and we have this idea of a fabric of space-time that is not the same throughout the universe. So this was revolutionary, and it is also a special theory of relativity. Relativity applying to how the world works. Special means it's only applying to the special case where we're moving at a constant speed. Einstein wanted to take this one step further. He wanted to generalize it so that we can be moving actually in an accelerating reference frame. So not just at a fixed speed, but changing speeds as well. So rather than a special theory of relativity, this was going to be a general theory of relativity. Now, early on in this, Einstein had a great thought called the equivalence principle. And to explain this, we once again have Marina. Now, Marina is very tired after doing a whole night of stargazing, and she's fallen asleep. And while she's fallen asleep, what we've done is we've put her in a box. Now, this box is kind of a metal cube. It has no windows. It has no way for Marina to see what's going on around her. And then we're going to do one of two things. So one of the things we could do is we take Marina, put her in a box, and put her in a spaceship, which is originally just floating outwards in space. So I want you to close your eyes and imagine that you are Marina. You are sitting in your spaceship, in your box. It is completely dark and you are floating. And then these rocket thrusters begin to fire. You get pushed backwards into the bottom of your box, and the acceleration increases and increases to 9.81 meters per second, which is the same as the gravitational force here on Earth. So you are being pushed into that box with the same force as gravity. So how does that feel? Well, we are feeling that all right now. We know what it feels like to be pushed down with the same force as gravity. So we could do that. Marina wakes up and she feels like she's being pushed down by gravity in her box. But she could also be on Earth as well. We could not put her in a spaceship. She's just on the Earth, feeling actually the same force pushing her down. So she has no way to see outside. So how does she tell which one she's in? Is she in the rocket moving away from Earth, or is she just sat on the planet? And the thing that Einstein realized here is that Marina has no way to tell, is she in the spaceship or is she on the Earth? We were ignoring vibrations and things like that here. And it actually turns out that in physics, there is no difference between accelerating in the spaceship and just being on Earth and feeling our gravitational force. So Einstein realized that a theory of how the universe works under acceleration is a theory of how the universe works because of gravity. So general relativity is a theory of gravity. And it gives us some really weird results, like the idea that if you are falling in a gravitational wave, if you're falling towards the Earth, you are not experiencing any forces at all. Gravitational force is a myth. And what we do to get around this is we have this idea of curved space-time. So we have this fabric of space and time being curved by anything with mass. So everybody here in this room, you are all curving space-time by different amounts. I had quite a lot of cakes earlier today. I'm curving space-time by quite a lot. But that's relatively tiny. You've got to have something really big like a star or a planet to curve space-time by a noticeable amount and have this kind of effect of gravity. But all that's happening when something pulls something towards something else under gravity is things are just following straight paths in curved space-time. So imagine you take a flat trampoline, you put a cannonball in the middle, so it's weighing it down, and then you put a ball on your trampoline, it's just going to follow this curved path down towards the middle. It's the same kind of thing happening in gravity. And if this disturbance in space-time changes, if we get our masses accelerating, that's how we're going to get these ripples propagating outwards, these gravitational waves. Now, to arrive at the idea of gravitational waves, Einstein first started with his Einstein field equations. So that's this set of equations right here, which describes general relativity. So this thing on the left, this is the Einstein tensor, which describes how space-time is curving. On the right, we have a bunch of constants, just numbers, and then we have the stress energy tensor. And this is telling us how matter moves in curved space-time. So there's a very famous quote by American physicist John Archibald Wheeler: matter tells space-time how to curve, that's what's happening over here, and then space-time tells matter how to move, and that's what we have on the left here. So Einstein needed to solve this equation to get something that looks a little bit like the equation that we associate with waves. But this is really difficult because it looks very simple here, but each of these terms has 16 components and they are notoriously challenging to solve. So we can only solve Einstein's equations for very simple cases or where we're making very big assumptions as well. So the assumptions that he made here was that we have something in space that is in a completely flat, completely empty universe, which we know isn't true, and has no kind of important mass on its own, which also isn't true. The strongest gravitational waves come from things like black holes, which have really strong masses. So this meant that Einstein wasn't actually sure whether gravitational waves could actually exist, and so were basically every physicist around the world. They didn't know, are these something real that we managed to kind of find in the mathematics, or have we made too many simplifying assumptions and the conclusions that we've arrived at are completely wrong? And it took quite a while to kind of arrive at the correct answer for that, about 100 years later, where we did finally detect gravitational waves for certain. But what actually makes a gravitational wave? Well, the answer to that is accelerating mass. So if you take something really big, let's go like a star or a black hole, and you accelerate it, the disturbance that it's making through space-time changes, and it's a bit like throwing a rock into a pond and watching those ripples propagate outwards, or driving a boat through a pond as well, and you get the wake going behind that. Accelerating mass creates these ripples through space-time, these waves of gravitational influence kind of propagating outwards. If I wave my arm like this is, my arm has mass, and I'm accelerating it, so I'm creating gravitational waves, but only very tiny ones. You've got to have really big things like black holes to make significant gravitational waves like we could detect. So by kind of 1916, this was the idea. Gravitational waves, they exist in the maths, they might not exist in reality. And this was the case all the way up until 1957 with the Chapel Hill Conference. So at this point, there had been quite a lot of discussion about whether gravitational waves do exist or not, as well as some refinement of the mathematics. But in 30 years, that's basically all that had been achieved. But that was going to change with this event here. So this was a conference about gravity and gravity physics held at the University of North Carolina in the United States. They had physicists all around the world come for a 6-day conference to talk about these things. And it was things all across gravity, all across general relativity, and that included gravitational waves. So there was debate, again, do these things exist, do they not exist, and also can they transfer energy as well? And one of the guys who was here was this guy here, Joseph Weber from the University of Maryland. Now, he wasn't an astrophysicist, he was an engineer. So he decided, actually, I'm going to try and build a detector to try and detect gravitational waves coming at us from distant space. He was going to try and be the first one to do this. So if we're going to try and imagine how do we detect a gravitational wave, first we need to understand what effect does a gravitational wave have as it passes through stuff. And it does something a little bit like this. So we have a GIF up here. The gravitational wave is moving from the screen outwards towards us. And we have this ring of particles around us like this. And these could be protons, they could be atoms, they could be bouncy balls. It doesn't really matter. What does matter is that gravitational waves are stretching and squeezing the space between these particles. And so if we take these two here, we're seeing the space between them stretching and squeezing. So in theory, all you need to do to detect a gravitational wave is have two objects like this. Let's go two bouncy balls. You have a ruler in between them. You wait for a gravitational wave to pass through, and then you detect how much they move by, and there you go, you've done it. But the challenge is actually how tiny these gravitational wave effects are. So to get an idea of this, we are going to look at some equations. It wouldn't be a very good physics talk if we didn't have some equations here. And this is the equation for gravitational wave strain, which is this quantity h. This tells us how powerful the gravitational waves are. And this relates to the length of our ruler. So let's say we've got a ruler of length 10, and then this tiny amount dl. So for a gravitational wave of strength h and a ruler L, it's going to move by this tiny amount dl as the wave passes through. So we need to get an idea of how big dl is. So let's take the case of GW150914, the first gravitational wave we ever detected. This came from the merger of two black holes with a total mass of 65 solar masses, 65 suns. And it happened in the incredibly distant universe, 1.4 billion light years away. And this was detected by the LIGO gravitational wave detectors. So if we calculate h for these parameters here, we get this number, 1 times 10 to the power of minus 21, or 0.0000000000001. So 21 zeros and then a 1. This is very, very tiny. So with our gravitational wave detector, how much did it actually move by? Well, LIGO has arms of length 4 kilometers or 4,000 meters. So if we plug that in, we find that these 4,000 meter long arms moved by only 4 times 10 to the power of minus 18 meters. This is 1,000 times smaller than the diameter of a proton, one of the fundamental building blocks of atoms. This kind of difference here is equivalent to changing the distance between the Earth and Alpha Centauri, our closest star system, by the width of a human hair. So it is a really, really tiny amount that we've got to try and detect from these gravitational waves. But Joseph Weber, he wasn't deterred. He was going to have a go anyway. And we'll talk about kind of what his approach was and how well that went. But I have been talking again for a little bit longer. Do you guys have any questions at this point? All good? Everyone's still following along? Yes. Just about. One person is. Okay. So the idea that Joseph Weber came up with was his Weber bars. So pretty simple. We get a big solid metal bar. He made these out of aluminium, and these are 2 meters long and 1 meter wide. And as gravitational waves pass through it, it's going to cause these atoms to stretch and squeeze in spacing. This is going to create tiny vibrations, and we can detect these with all of these little sensors, which are piezoelectric crystals, which are very good at measuring these tiny vibrations within the cylinder. But again, really, really faint detection that we need to make. So what they do is you have your cylinder here suspended by this suspension. You isolate it from noise with things like foam matting and rubber pads. And it's in a vacuum chamber as well, so we have no air around it that's going to influence our bars as well. So Weber set up 2 of these things. He had one of them in Maryland. He had another one 1,000 kilometers away in Chicago, so that if a gravitational wave comes through, it's going to be detected in both of them together. So you'll get the same signal in both. If you get a signal that only in one of them, and then maybe this is something local, like a truck going past, somebody stamping or knocking on the container, anything like that. So he set these up pretty quickly, and 12 years later, in 1969, he announced he had detected gravitational waves. He had found these signals coming from space with his Weber bars. And this was incredible, and it was met with excitement and praise by the entire astronomical community. So other groups around the world constructed their own Weber bars in Scotland and Italy and Germany, Japan, and across the United States. But none of these other detectors managed to find anything. And at the same time, theoretical physicists were looking at Weber's results and finding something that looked a little bit strange. So he was detecting, every time the Milky Way came overhead, he was seeing all of these gravitational waves. And they worked out for these gravitational waves to be coming from the Milky Way with the amount that Weber was saying, the Milky Way would have lost so much mass that it would have dissolved away millions of years ago. So that could not be the case. So there must have been something wrong with his detections. And none of the other Weber bars operated by anybody else managed to detect anything at all. There were even some that was much more advanced than his original detectors. For example, this one here, this is the Explorer experiment at CERN in Europe. This was not only isolated and in a vacuum, but it was cryogenically cooled to just a couple of degrees above absolute zero. And they reckon that this was about 10,000 times more sensitive than the original Weber design. But it operated for 20 years, and in this time it detected absolutely nothing. So what was Weber detecting? Well, likely just noise. Probably nothing at all, but he was very generously interpreting this as detections. And sadly, that when the astronomy community kind of refuted his claim, said, no, this is not what you're detecting, he only doubled down and refused to say that he was wrong. His career, sadly, kind of took a bad turn because of this. And even until his death, he claimed that he was the first one to detect gravitational waves with these Weber bars. But today, he is remembered not for being wrong, but actually for being one of the pioneers of gravitational wave detection. He was the first person to think, let's try and detect them, let's try and build a detector, and he's credited for inspiring other astronomers, other engineers, for the detection efforts that we eventually managed to achieve. So this was pretty disappointing by the end of the 1960s, but come the 1970s, hope was renewed once more with the discovery of the Hulse-Taylor Pulsar and our first indirect evidence of gravitational waves. So we've got a lot of words up here at the top of the screen. Let's start with the simple ones, Hulse and Taylor. That's these two guys right here. Russell Hulse on the right, Joseph Taylor on the left, two astronomers at the University of Massachusetts in the United States. And what they observed was the first binary pulsar ever discovered. Now, a pulsar is a type of rapidly rotating, highly magnetized neutron star. So remember, we were talking about the life cycles of stars earlier on. We're looking at this cycle here, where we get to our city-sized, incredibly dense object. Now, if you start with a red supergiant that is very large, it's got a strong magnetic field, and it's spinning somewhat slowly, and you crush it down into something really small, like a neutron star, in just the right way, it is going to spin up very, very quickly. So we can have neutron stars that are spinning at up to 1,000 times per second. So super fast, whizzing around. And they can have a really strong magnetic field as well. And if we have both of these things together, then what we're going to get is radio waves being channeled in these jets along the magnetic field lines. And this gives us something a little bit like this. So this is a pulsar spinning around. It's got its radio waves, which are given by these yellow cones here. And it's kind of facing away from us, and then it flashes towards us, and then turns around, and then it flashes back towards us as well. So this is what we call the lighthouse effect, where we're getting these flashes of radio waves. And these kind of rotations are super stable. So we're seeing this very rhythmic pulsing of radio wave emission coming from these pulsars. And some of them are stable enough that they rival the best atomic clocks here on Earth. So this had already been discovered at this point. But what these guys found was two neutron stars orbiting around each other in a binary pair. And one of them was a pulsar. Oh. And the thing that told them that it was indeed a binary system is that sometimes this pulse would arrive slightly too soon, sometimes it would arrive slightly too late. And they used the 305-meter Arecibo radio telescope in order to make this discovery. So they found this. That was really cool on its own, but because it was a really stable pulsar, they were able to monitor it over years and see how that signal was changing over time. And they noticed over a period of about 3 years that the orbits of these two neutron stars were slowly getting closer. The orbital period was decreasing. And so the neutron stars were somehow losing energy. How do we lose energy from an orbit? Well, general relativity says we lose them via the emission of gravitational waves. So the stars are emitting gravitational waves, and so they're getting closer together. They calculated how much they would be shrinking, how much they would be getting closer together by emitting gravitational waves. This was within 0.5% of what they measured in reality from these neutron stars. So this was taken by astronomers as the first indirect evidence that gravitational waves existed. We had found something that shows that maybe these are being emitted by this binary system. But this wasn't a direct detection. We weren't at that point just yet. Now, to get there, we needed a new piece of technology, which was the gravitational wave interferometer. And this is just a really fancy way to measure distances on Earth. So the way an interferometer works is we start with a laser, a little bit like what I've got here, but much more powerful. We shoot this down a tube until it hits a beam splitter. And this sends half of the laser off to a side, and then the other half of the laser passes straight on through like this. So if we follow the path of this left-hand laser beam, it goes all the way down this length, and then it bounces between these two test masses. Test mass are just these kind of suspended mirrors. So we're bouncing the light between the mirrors in these light storage arms, and then eventually it comes back to here. It recombines with the other laser beam here at the photodetector, which is just a camera. And we set this up so that the path length traveled by these two light beams are almost exactly the same, apart from they're just going to be slightly out of phase with each other. So this gives us something called destructive interference. We've got a diagram here. So if you've got two waves of light here, and you overlay them on top of each other, and they are identical, then these waves are going to combine together to create something that is even stronger than what we originally started with. But if we have them so that they are out of phase, if they are mirror opposites of each other, like this, then the peaks and the troughs are going to add together and cancel out. So we're actually going to detect absolutely nothing at all. So when your light recombines here, if nothing is happening, then you should get absolutely nothing being detected. But then as the gravitational wave passes through, it's going to change the length of one of these arms. The light is going to travel a slightly different distance, and so they don't perfectly destructively interfere. Then you're going to detect something here where there would otherwise be nothing, and you have made your gravitational wave discovery. So this was kind of developed by quite a few people independently in the early 1970s. The credit often goes to two astronomers called Robert Forward and Rainer Weiss, who built the earliest prototypes, which are just kind of these few meter-long gravitational wave detectors just on bench tops and in labs. But they knew right from the start that they need to actually be quite big in order to make any kind of detection. And there's two reasons for this. First of all, let's go back to this equation for the gravitational wave strain. The longer we can make L, sort of the length of our detector, the bigger we can make DL, the tiny change that we need to measure. If we make this tiny change as big as we can, we've got the best chance of measuring. So that's why we have these kilometer-sized gravitational wave detectors today. And the other thing is we need to tune our gravitational wave detector to the exact frequency that we want to measure. It's a little bit like if you have an antenna that you're detecting radio waves. Anyone here that has driven an old car, you might know that you have these really long antennas. But now we have really short antennas because we're looking at different types of radio waves to what we were decades ago when we want to listen to our radio, listen to Brian FM, whatever you want to do. And it's similar with gravitational waves. So we want to try and detect the strongest gravitational waves that we can, which come from the mergers of black holes and neutron stars. And these have a frequency of about 100 hertz, so they are orbiting around 100 cycles per second. And this corresponds to gravitational arms measuring 750 kilometers in length. This is way bigger than anything we can actually build on Earth. So we cheat a little bit by having these light storage arms. So we can make the light travel 750 kilometers, even though our arms are only a few kilometers long. But to make this easier, we want our arms to be as long as we can. So this was the kind of idea that was pioneered in the 1970s. Then throughout the 70s and the 80s, there was a lot of development into the technologies needed to make these detectors. And in the 1990s, we finally had 3 big projects ready to break ground around the world. So this is the status of gravitational wave observatories as we have them today. We have our 2 LIGO detectors in the United States. We have GEO 600, which is in Germany, Virgo in Italy. CAGRA is actually a very new one, started operations in 2020, and that's in Japan. And we have a planned detector in India as well. But the first 3 were these 2, GEO 600 and Virgo. So GEO 600 is an interferometer in Hanover in Germany. This has 600-meter long arms. It was started in 1995, finished in 2002, same year as I was born. And we then had Virgo, This was in Italy, collaboration between French and Italian teams. This has 3-kilometer long arms, again finished in 2003. And then the 2 LIGO detectors started mid-90s, finished 2002 as well. So these were all finished about the same time. We had these 3 gravitational wave detector sites, but this is the one that was then going to go on to make the first ever detection. So that's what we're going to talk about next. But again, I'm going to check in with you guys. Do we have any questions so far?
The light's got to go and back control.
Yeah.
Each time the light changes direction, it's got to stop. Starting people on the errors built in there.
Yes, exactly. So one of the biggest sources of errors and lack of sensitivity in the gravitational wave detection was actually these test masses. So we need to have these mirrors suspended so they are free from all vibrations. Essentially, they're just almost hanging there floating so the light can hit it and bounce off with as little disturbance as possible. If they are wobbling around even the tiniest amount, they interfere with our light, and it's going to give us all kinds of bad signals.
How can you do that? When you measure such as time,
Yeah, so we do statistical analysis. So we look at the signal that we detect, and we go, actually, what is the chance that this could be fake? What is the chance that this could be just random from these tiny little vibrations? And the threshold that we have is 5 sigma. So it needs to be above a 99.99994% chance that this is a real detection for us to say we've made a detection. Because there is a lot of uncertainty that can happen here. And there certainly was in the early versions of these detectors. Yeah, go for it.
Notice all the interferometers are in the northern hemisphere.
Yeah.
Is there any reason why none at the southern hemisphere?
Yes, it's just because these interferometers were very expensive to make. These were multiple $1 million projects, tens of millions, hundreds of millions sometimes. And so not many places could actually afford them. So obviously the US has a very big scientific community, so we have lots of universities getting together as well as government agencies to build them. These ones in Europe were collaborations between, again, tens of universities coming together to build these detectors. And so in the southern hemisphere, there's just not as many institutions, there's not as many kind of people that can work on these and fund them. And that's kind of the only reason why there aren't so many. There was plans in the future to maybe build another LIGO detector in Australia, but the Australian government didn't want to put any money towards it, so that's kind of planned for India instead. Yeah. Okay. So, yeah, go for it.
So you said what you were going to try and affect one of the arms in order to, I guess, get a reading on that destructive.
Yes.
How can you control that? How can you create a gravitational wave on one line and not the other?
So you can't. So it's so the idea is our 2 arms are perpendicular to each other. So in an ideal scenario, if a gravitational wave comes along, let's say it comes along in this direction here. So it is traveling down this length. Here, it is going to create the maximum change that it can in this arm. But here, it's actually not going to change the length that the light travels by any time, any period at all. Because gravitational waves distort space kind of around them, not in the direction that they're traveling. So if you've got one that's just coming down here, you're only going to get a change in here, and so your light is going to change kind of how they're traveling with respect to each other. That is the idealized scenario that never actually happens. So maybe you've got a gravitational wave that comes in at an angle like this. So it does a little bit of something here, it does a bigger bit of something over here, but the end result is still the same. The end result is still that this is not 0, you still get a detection. Yeah, does that kind of make sense? Yeah. Okay. So this was the detector that manages to make the first gravitational wave detection, but this took 13 years from when it became operational. So it started operations in 2002. From 2002 all the way up until 2010, it operated for 10 years and it detected absolutely nothing. At this point, the LIGO detectors were put on offline. They were kind of upgraded and fixed a little bit in a pretty major way, in fact. So it was almost a complete overhaul of the entire system. So we had laser power being upped from the 10 watts to 100 watts, 20 times more powerful lasers. We had new detectors, which were much more sensitive. And the biggest change was actually in these test mass mirrors that the light was being reflected off. So what we were talking about earlier, where you have originally this little mirror like this, with one little set of suspensions and a single pendulum weighing 11 kilos. That was massively upgraded to this 4-segment pendulum to try and reduce our vibrations as much as possible. Even the smallest vibrations would still be larger than the gravitational waves by about 1,000 times. So this was a massive improvement, massively improved the sensitivity of the gravitational wave detectors. We have an image up here. This is one of the detectors that you can see here in the vacuum tube. So you can see just how complicated these instruments are. So they had all of this installed, and on the 13th of September 2015, they were doing the final series of tests that they needed to do. So they were testing what kind of vibrations would produce different noise effects within the detectors. So they were stamping around, they were banging on the detectors, seeing what kind of signals that they were creating. This took much longer than it was meant to, as do all things in science. So they were there until about 4 o'clock in the morning, at which point they went home and everybody went to bed, leaving the detector on to run. But this was still 4 days before the official observing run was going to be. 50 minutes later, we had the first ever detection of gravitational waves at 4:50 in the morning, just under an hour after everybody had gone home. So this is what the detection looked like, passing through the 2 detectors in about 0.7 milliseconds. It lasted 7 milliseconds in total, lasted 0.2 milliseconds. And this was from the merger of 2 black holes. So we can see the different phases of the signal here. So here you have 2 black holes kind of getting closer and closer, losing energy as gravitational waves as they do. As they get closer, they move faster and faster. So the gravitational waves become stronger. So we get our signal becoming stronger like this, until eventually we get the strongest signal at the merger phase. The 2 black holes collide. And this is a bit like taking 2 cups of water and pouring them together into one bowl. So at this point, they just merge. They form a new black hole, which stabilizes very quickly in what we call the ring down phase, like this. So we've got our identical detections from the 2 different detectors. And astronomers were alerted within 3 hours that this was a detection. And then within a couple of weeks, we had our statistical analysis that confirmed with a confidence of 5.1 sigma, or 99.999994%, that this was a real detection. We had detected gravitational waves. And what had done it was a binary black hole system merging 1.4 billion light years away. So by analyzing the shape of this waveform here, we can determine that we have 2 black holes, one weighing 30 solar masses, the other one 35 solar masses, merging together to create something weighing 62 solar masses, and this happened well over 1 billion light years away. So we detected the signal that actually happened 1 billion years in the past. Now, what you might notice is that these 2 numbers, 30 plus 35, does not equal 62. We've got 3 solar masses that has disappeared. So where has it disappeared to? It's become gravitational waves in this final 0.2 seconds of that merger. So we've had the equivalent of 3 suns being turned into gravitational wave energy in less than a second. So during this time, this gravitational event was about 500 billion times more powerful than the entire light of the Milky Way. That is how incredible these things are. And this was a massive event in the news. People were really excited about it all over the world because this had taken 100 years from the formation of Einstein's theory of general relativity in 1915, all the way up until the first direct detection in 2015. Now, this was only made by those 2 LIGO detectors. Virgo at the time was offline for its own upgrades, and Geo 600 just wasn't sensitive enough to make this detection. But the technologies that went into LIGO to allow this to be possible were as part of collaborations between all of these detectors. So the technologies tested and developed in these other 2 made their way into LIGO, and so this really was a global effort to make these first gravitational wave detections. But this was just the start. And from here, we kind of only started detecting more and more. And today we have made over 300 gravitational wave detections so far. Now, we make gravitational detections in observing runs. So we turn the detectors on for a bit, see what we can find, turn them off for maintenance and upgrades, then keep going like that. So in the initial observing run, LIGO made 3 detections of gravitational waves. Then it was joined in 2017 for the second observing run by the Virgo detector, and here they made 8 detections in total. And then it was turned off again. They put a lot more upgrades into it, so that in the third observing run, we made just under 80 detections in total. This finished slightly prematurely in 2020 for obvious reasons. And from 2020 to 2023, it was upgraded. So the initial advancements were made to kind of turn LIGO from initial LIGO to advanced LIGO. And then between 03 and 04, we went from advanced LIGO to LIGO A+. So this about doubled its sensitivity. And in this time, it then has managed to detect about 200 gravitational wave observations, more than double what we made in the first 3 runs combined. And this is still ongoing. The run is scheduled to end in November, in about a month's time. So to give you an idea of the sensitivity change over this time, we kind of compare gravitational wave sensitivity by looking at how far away can we detect the kind of weakest mergers. So these are the mergers of neutron stars. And to start with, in 01, this was 250 million light years away from Earth. And now we have more than doubled that to 04, 550 million light years away. And this means that we are probing 7 times more universe around us to find these events going on out there. Now, what have we achieved in all of this time? We've had 10 years, 1 decade of gravitational wave science. What have we learned? Well, to talk about this, I'm going to tell you about 3 gravitational waves in particular. This one right here, GW 170817. This one right here, GW 231123. And then this one here, discovered this year, 250114. So, GW 170817, undoubtedly the most important gravitational wave that we've ever detected, because this was not formed as part of the merger of black holes. Almost all of these detections have been black holes merging together. This was actually the merger of 2 neutron stars, so slightly smaller star corpuscles. Now, the thing about black holes is they are black. When they merge, they produce a huge amount of gravitational waves, but that's it. Neutron stars are not. When neutron stars merge, they produce enormous explosions called kilonovae. And so when this gravitational wave was detected, astronomers around the world were able to follow up with their observatories, and they found, with 70 different telescopes around the world, this kilonova that had appeared in a distant galaxy, NGC 4993. So here's a series of pictures taken with the Hubble Space Telescope, starting very bright, and then it just kind of fades away. And this was our first ever example of multi-messenger astronomy. Up to this point, we can do astronomy with light, we can do astronomy with gravitational waves, but now with this event, we're able to do it with both. We can see one thing in both gravitational waves and invisible light, and this gives us so much amazing science that we can do with it. So just from this one thing, we were able to learn a lot about neutron stars, kilonova, gamma ray bursts. We were able to test some of our models of the universe and our models of astrophysics as well. And to give you an idea of just how important this was, the paper that was released about these multi-messenger observations was authored by 4,000 astronomers, which is a third of all astronomers around the world were involved in this detection, which I think is really cool. But in terms of testing our models, this was also really important with the biggest gravitational wave detection that we have made so far, 231123, where we have these colossal black holes weighing 130 solar masses and 103 solar masses merging to form something that is 225 solar masses. And what's quite interesting here is that when stars die, they create black holes if they are big enough. But there is a limit on how big stars can physically be. And so there is a limit on how big black holes can physically be as well. So we're not too sure on what this is, but it could be somewhere between 60 and 100 solar masses. The idea here is that maybe we had 4 black holes which have merged to form 2 black holes, which then we've seen merge to form this one bigger black hole, what we call hierarchical merging, which is a pretty cool thing to find evidence of out there in our universe. The other thing that we noticed is that these black holes were spinning a lot, actually close to the maximum amount that they can spin as defined by general relativity. So this is a really extreme scenario, highly spinning black holes, huge masses, so it's testing our theories and our simulations to their limits. So you have a simulation down here. It is meant to be a video, but it hasn't worked for some reason. But this is kind of helping us improve how we are modeling our gravitational wave detections and the amounts that we can learn from them as well. And this was done very recently with GW 250114, the clearest black hole merger that we've detected to date. And this is quite cool because this was a scenario that wasn't too different from that first ever binary system merger that we detected in 2015. So we had 2 black holes merging to create something that was 63 solar masses, and this happened just over 1 billion light years away. And here you can see the difference between the two signals. So in 2015, we have lots of this spiky purpley noise. In 2025, very little of it. And the signal to noise ratio was more than 3 times better. So we've got a really nice, really clear detection, which allows us to do lots of really high precision science. So one of the things we were able to test was Hawking area theorem, one of the great ideas of Stephen Hawking, which is that when black holes merge together, their surface area cannot get smaller, it can only get bigger. And we have had some evidence of this before, but this was the most conclusive evidence that we had of it so far. And the other thing that we were able to see was right at the end of our gravitational wave signal, we have in the ring down phase where the black hole is settling, actually overtones. So this is a bit like if you take a bell and you strike it with a hammer, you're going to get your kind of baseline bong coming out of it, but then you've got these other kind of tones layered above that, just like in all musical notes. And so this is what we have other tones layered above it, and for the first time we were able to detect one of these overtones right here. And this turned out to be exactly as predicted by something called the Kerr solution, which is a mathematical way of describing a black hole based only on its mass and its spin. So this is confirming to us that general relativity and our models that we base off it are, as best as we can tell, a really good, accurate description of our universe. So this is just 3 examples from the last decade, but we have also found loads of other great things like the lightest black holes detected, really asymmetrical mergers where you have a big black hole and a tiny neutron star, and all kinds of things like that. So there has been a lot of great science that has been done so far, but we're going to talk about what's next as we go on into our next slide. Once again, guys, any questions at this point? There are no stupid questions. Go for it.
If we stand here and a black hole passes through us,
Yes.
how happen to be standing on the bathroom scale?
Sorry, what was the last part there?
If I happen to be standing on the bathroom scale,
Yeah.
my weight wouldn't change,
No, it wouldn't.
but I would become slightly more dispersed.
Exactly, yeah. So,
Back again.
exactly. So your atoms will become slightly more stretched out and then slightly more stretched in, but this is a really tiny amount, so nothing that you'd ever realize.
Even though it's called gravity, it's not to do with the pull of the Earth on your...
No, so it's actually to do with space and time itself stretching, which is, yeah, very weird to think about. But it is the space that is stretching, not necessarily the gravity of Earth. But if you are close to a black hole like this, if you're, say, the same distance as the Earth from the sun, from this black hole merger, you'll be ripped apart by these gravitational waves. They are that strong. But then it's just when you get away from it, billions of light years, then they become really, really faint, so then it's much harder to detect them.
What is it about the source of the collision?
Yeah. Yeah, great question. So how do we know about the source of the collision? Like what actually creates these waveforms? So what we do is, I guess this is a good description of it here. So the purple line, which you can just about see against the dark background, is what we actually measured. So we measure these oscillations getting larger and larger, getting smaller and smaller, and kind of coming together like this. And then we fit this model to them. So we fit this curve, which is the green line, against that, which is what we are producing with a computer simulation. So in the early 2000s, there was a lot of work that went into solving the equations for general relativity for black hole mergers. So what does the waveform actually look like? And it turns out that different distances and different masses of black holes give us different signals about what's happening. So we can look at what's happening over here, and this is telling us about the masses of these 2 original black holes, just by fitting what is the best model that we can to our signal here. And then towards the end, we can look at how it's settling down to get an idea of how big does our final black hole end up. And we can see how the phase advances over time, and kind of the difference between each of these peaks to tell us all kinds of things, including the distance to them as well. So yeah, just looking at the signal, trying to match up to it with our models.
And it's the same.
Yeah, it's the same for the neutron stars as well. So a neutron star merger is going to give us a subtly different pattern here to the black hole merger. And that's how we can detect, okay, these were neutron stars, these weren't black holes. Yeah. Yes, go for it.
Can gravitational waves join other gravitational waves? I mean, bigger gravitational. How do you know it comes from a single source?
So the answer is yes. These are waves, and waves can interfere constructively, like we talked about earlier with the gravitational wave interferometer. They're not going to in this case, because these are quite rare detections. So you've got kind of These signals that are happening, we're detecting one every few days at the moment. So they're not overlapping enough that we're going to get this interference in a meaningful way. There are some gravitational waves coming from the early universe. So we think the Big Bang would have emitted quite a lot of gravitational waves, and we think that colliding galaxies in the early universe would have emitted a lot of gravitational waves as well. And these will be permeating throughout the entire universe, kind of a static background, and then these could then interfere and then give us all kinds of wacky signals like that. But for these kinds of gravitational waves, we're not likely to see that. And then there's a question there. Yeah, for yourself.
So the two stars collide, you get a corona or two black holes inside of the black hole, and what happens if a black hole and a neutron star?
What happens is a black hole and a neutron star merge. We're not too sure. We've not seen too many of these things. So there's some coincident observations and some theory to suggest that we might get this little burst of radiation, maybe in form of gamma rays. We've not been able to actually detect anything concrete so far in these mergers. So it could be nothing. It could be a little bit of something. Certainly nothing like a kilonova, for sure. Yeah.
But it still is measurable gravitational wave.
Is what, sorry?
It's still measurable.
Still measurable, yes. Yeah. Yeah.
Black holes something being seen.
Where do they go? Okay, that is the question. The answer is we don't really know. But I guess the best way to think about it is that anything that goes into a black hole becomes more black hole. So it gets pulled right in towards that singularity, and it just adds to the mass of that singularity. So we have this infinitely small point in the center. If you fell into a black hole, that now grows in mass. It becomes that much stronger by however much you weigh. Now that is our mathematical description of a black hole. From all of the observations we made with gravitational waves, this is a really good description of a black hole. That doesn't mean that it's an accurate one for what's actually going on inside it. This is just how it works in the maths, and this has worked for us so far. So as far as we know, you join that singularity and you just become more black hole.
Does black work not?
Yeah, very slowly. So from something called Hawking radiation, the black hole very, very slowly evaporates off from the surface. But this takes, for most black holes in the universe, trillions or quadrillions of years. So much time that, nothing that we've actually detected so far. But we think that from quantum mechanics, black holes do slowly vaporize off from the surface.
What is that really dense singularity? Yeah.
So it just slowly vaporizes. It gets smaller and smaller and smaller until it disappears. It is a lot to think about, yeah. Okay, so let's talk about kind of where we are right now and what's going to happen in the future as well. So we have 3 pretty decent gravitational wave observatories. So we have the 2 LIGO detectors in the United States, we have our Virgo detector in Italy, and we have the Kagra detector, which is very cool. It's under a mountain in Japan as well. Now, I'm not including Geo 600. This has failed to detect any gravitational waves so far just because it's a little bit too small. So now Geo 600 is used to test new technologies, not to actually detect these gravitational waves. And so we've got this kind of picture like this. Virgo and Kagra, these are 3 to 5 years behind LIGO. So this is still our most advanced gravitational wave detector. LIGO is going to be continuing to advance, and then these ones are continuing to become more advanced as well. Hopefully they'll catch up eventually, but overall we're going to make these as accurate and as sensitive as we possibly can. The next upgrade package to LIGO is called LIGO Voyager. Once they finish observing next month, they're going to start installing this, and they're hoping to get it twice as sensitive as what they have it right now. Now, I did mention earlier, we have this plan to build a detector in India as well. So this is an identical one to one of these LIGOs, so they're going to put it over here. It is part of a partnership between the United States and the Indian government, and they have greenlit the project. They've allocated some funds, and then they've started constructing it. And the reason we're doing this is that we want a network of gravitational wave detectors going all over the world, because we want to try and localize our sources in the sky. So if we have one single gravitational detector, let's go for LIGO Hanford over here, and the gravitational wave passes through, we can detect it's there, but we have an area of about half the sky where it could actually come from. When we have 2 detectors, then we're able to localize it a little bit better. 3 detectors, a little bit better. If we can do a network of detectors across the world, then we can have a really good idea of where this gravitational wave is coming from. And we want to do this because we want to do much more of this multi-messenger astronomy. We want to see loads more of these binary neutron star mergers, work out where they are in the night sky, and then get our electromagnetic observations as well. And we have some specific telescopes that are going to be used for that. So we have here the Vera Rubin Observatory. It is the world's newest big telescope. This measures 8 meters across for the primary mirror. You can see a person here compared to the telescope. And this is a really cool piece of technology. It has a 3 billion pixel camera, the largest camera ever made. And that means it's got a huge field of view. So it scans the entire night sky once a week. And it's doing this in massive kind of detail to try and find anything that's changing in the night sky. So things like comets and asteroids, supernova, kilonova, all of these transient things in our night sky. So we're thinking that the best thing to try and find the observations from our gravitational waves is maybe Vera Rubin. And in fact, LIGO and Virgo have extended their current observing run to coincide with the start of the observations for this telescope, just so that maybe we can find something out there in the night sky. And then we do have telescopes that are constructed specifically for these follow-up observations. So here we've got the Black Gem Observatory. We have these 3 things over here. And this is an array of telescopes that is linked to a network with these gravitational wave detectors, so that when these detect something, they have an idea of where it is in the sky. These telescopes can scan that bit of the sky and see if they can try and spot something. So we can try and get our multi-messenger observations as early as we possibly can. But it's going to be pretty difficult to do that. We've only detected, I think, 3 binary neutron star mergers in the last 10 years. So what we actually need are some better detectors. And this is the next generation, the 3rd generation of gravitational wave detectors. And there are 2 plans for these. So the first one is the Einstein telescope, which is this triangular design here. The plan is to have this ready in about 2025. It's got these 3 detectors kind of nested within inside each other, with arm lengths of 10 kilometers long. So having longer arms means it's going to be more sensitive, and we're hopefully going to make much more detections. And this is what it looks like. We're also going to put it underground to try and reduce our vibrational noise even more than what you have on the surface. And this is a European collaboration. So institutions from across Europe are coming together to try and build this Einstein telescope. But in very European fashion, they can't decide where to build it. The Germans want it in Germany, the French want it in France, the Italians want it in Italy. So someone's going to try and knock their heads together and get them to actually decide somewhere to put it. And the other one that we have is Cosmic Explorer, which is an American project. This is the kind of classic L-shaped detector, a bit like LIGO, but you can see here, 40-kilometer long arm, so 10 times bigger than what we have already, and so much more sensitive as well. And then we'd build these, again, 2 of them across the United States, a bit like those 2 LIGO detectors. So we'd have 3 gravitational detectors going into the 2030s and the 2040s, hopefully. Although trying to get science projects funded in the United States is a bit difficult at the moment. Hopefully they'll sort that out in a few years' time. And the thing that's kind of really good about these is they are going to have a much lower amount of noise. So this is what the noise curves look like for these gravitational wave detectors, where we've got our different frequencies over here, and we've got our noise here. Basically, the bigger this is, higher up here, the worse it is. So you can see advanced LIGO down here, pretty high. We upgrade to A+, we've got the next one, Voyager here, then the Einstein telescope and Cosmic Explorer, nice and low down here. And we can see they've got access to a much wider frequency range than these ones up here. So we're going to detect a huge amount of detections. We're reckoning about 10,000 detections per year, compared to the 300 that we've made in the last decade. And 100 to 1,000 of those are hopefully going to be binary neutron star detections. So we're going to take multiple of these per day, and hopefully have routine multi-messenger astronomy, which would be really cool. And the science goals are just insane. Because when we're looking at black holes, we're going to see these going all the way back to the early universe, just after the Big Bang. So we're going to be able to probe the Big Bang, how the universe expanded after that, looking at black hole mergers in the early universe as well. We're going to be able to do lots of messenger astronomy, teaching us about neutron stars, kilonova, and allowing us to measure cosmological parameters as well. So neutron stars allow us to measure distances in space really well. And this is kind of what my project was working on, trying to model what kind of accuracy can we come up with these detections for these next generations of gravitational wave observatories. So this will be revolutionary. It will be the real start of a massive field of gravitational wave science if the Europeans can agree where to build their telescope, and if the Americans can decide to actually fund this thing here. Now, if we look at these gravitational wave strain curves, you'll notice that when we get low to this 10 down here and kind of lower, they all shoot upwards. And this is because of seismic noise. So this is because of the vibrations of the Earth, basically washing out any gravitational wave signals over here. Einstein telescope being underground is a little bit better at this, so we can see it's got kind of the best sensitivity at low ranges. But there's a lot of things that emit gravitational waves that will be quite strong, but they're really low frequency, they're way down here. And we're just not going to detect those at all on Earth. So to be able to get around that, we've got to go to space. So we have two kind of projects that are looking at detecting gravitational waves in space. The first one of these is LISA, the Laser Interferometer Space Antenna. And I think this is really cool because we've got 3 spacecraft separated by about 2.5 million kilometers that are firing these infrared laser beams between each other. And they're measuring the distances between each other to then measure as a gravitational wave passes through the tiny little vibrations, the tiny little variations in that length. This is a project between the European Space Agency and their various collaborators. And these gravitational wave spacecraft, there's no way to keep them fixed in constant positions. So actually, they are going to have to be constantly measuring how far away they are from each other, really, really accurately, to be able to make any sort of accurate detections. And then as our little test mass mirrors, we've got these free-floating gold cubes, which are being shielded by the spacecraft around them. These are reflecting the lasers. So 2 kilograms of gold right there. And it's just floating there in space, completely weightless. This is going to trail after the Earth, going to be pretty enormous. So not only is it going to be very sensitive, but by having very big detector arms, we're going to be probing really low frequency gravitational waves. So we're expecting to find things like black holes orbiting around each other, but not quite close enough to merge within our own galaxy. We might also find white dwarfs, again, orbiting around each other up to the point of merger, and potentially looking at really big black hole collisions in the early universe as well. So entire galaxies merging together and the supermassive black holes merging in those as well. So it's going to unlock a completely new type of gravitational waves for us to explore. So the idea is to have this launched in 2035. The European Space Agency has selected this as one of their big projects that they're going to try and do. And so we have prototypes for some of the detectors already being built. And I think of these kind of new projects, this is the one that is actually the most likely to actually end up happening. So that will be pretty cool. 2030s is going to be a great time for gravitational wave science. And the other thing that we have going on as well is pulsar timing. So remember, about 45 minutes ago, we briefly talked about pulsars with this Hulse-Taylor Pulsar that was discovered. So once again, these are rapidly rotating, highly magnetized neutron stars, and we're getting these regular pulse radio waves coming from them. Now we can imagine these almost as enormous interferometer arms stretching outwards into space. We've got a pulsar over here, and the pulses are coming towards us. As a gravitational wave comes through, it's going to stretch that space. The pulse is going to arrive at a slightly different time, and we've detected our gravitational wave. But once again, it's a very tiny detection. It's very hard to do this. And so rather than looking at just one pulsar, we have these pulsar timing arrays. So you're looking at a network of between 20 and 50 pulsars and monitoring what time the pulses are hitting with big radio telescopes like this one. This is part of a European collaboration for pulsar timing. And over time, you can build up this evidence of gravitational waves. And we think this is where we're going to find something like a gravitational wave background. So from enormous black holes merging in the early universe, we're going to find lots of these gravitational waves all over the place and constantly affecting our pulsar timings. Now, in 2020, we had the first evidence reported for gravitational wave detections. And this evidence has been improving in confidence over the last few years. We are not quite at the point where we can say we have detected these things, but we are almost there. Give it probably a few years, and I think we will have made these detections with our pulsar timing arrays. Now, we're not able to detect exactly what are producing these gravitational waves. We're not able to detect where they are coming from, but we can only kind of find out that they are there. But these kinds of improvements can be made in the future. So if we manage to be confident in our detections, we can look at improvements to pulsar timing to try and find the sources of these signals as well. And as we reach the end of our talk, combining all of the things together, we are looking at a full spectrum of gravitational wave emission. Not only using our ground-based experiments to look at the mergers of compact objects, but also going into space to probe different types of black holes and white dwarfs, using our pulsar timing to look at merging supermassive black holes, and even looking at properties of kind of the afterglow of the Big Bang itself to try and detect these gravitational waves. And this is the thing that is going to be incredibly influential going forward, looking at the entire universe, not only with electromagnetic waves, but also unlocking the gravitational universe. We are only just beginning to do this over the last decade, and as we go into the coming decades, I think there is going to be a huge amount of science waiting for that out there for us to discover it. So, we are now here at the end of our talk. Thank you guys very much for coming along. I thank you for all your questions. It's been a great audience.